mechanical energy is nothing but the sum of potential energy plus kinetic energy. If you apply large amount of force, there will be large displacement, x will be more. If you apply less force, the displacement will also be less. The total energy of isolated system remains constant. Energy can neither be created nor be destroyed. Hello everyone, I am Nishma Nanjamma, Faculty of Physics in Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Welcome back to my session 4 on chapter 6, Work, Energy and Power. In this session 4, we shall discuss what is potential energy, derive the expression for potential energy by a spring, and also we shall see what do you mean by law of conservation of energy. So begin the session with potential energy. In the previous sessions of chapter 6, we have studied what do you mean by energy. Energy is the capacity or ability of the body to do work. And we have discussed in the previous session about the mechanical energy. Mechanical energy is nothing but the sum of potential energy plus kinetic energy. It is the sum of potential energy and kinetic energy. In the previous session, we discussed about kinetic energy and its expression. Kinetic energy is the energy possessed by the body by virtue of its motion. And then what do you mean by potential energy? We had discussed about potential energy in a previous session, and we'll discuss in more detail about the potential energy in this session. So potential. What do you mean by potential energy? It is the energy stored in a body. It is the energy stored in a body due to its position or change in shape is called potential energy. I say the child has the potential to score well in the exam. I'll say the child has the potential. What do you mean by potential here? That is the ability, capability of a body to do something, He has a potential to perform the work. He or she has a potential to score well in the exam. Potential means it is the capacity or capability of a body to do something, to perform some work. It's called potential energy. For example, if I say a water stored in a tank, suppose you have a ground. From a ground at certain height h, a water has been stored in the tank. So this is your ground. From the ground level, a water has been stored in the tank at certain height h. So from the ground, we are doing some work in order to lift the tank against the gravity. So here in the ground, in the earth, you have the effect of gravitation. So we are doing some amount of work in order to applying some force to lift this tank of height h to certain point. So this work done is stored as a potential energy where the velocity is zero. Once the height starts to decrease, the potential energy, the water starts to flow from the tank. Flowing of water is an example for kinetic energy, isn't it? A water starts to flow from the tank. That means potential energy is lost. The water is gaining the kinetic energy. The potential energy loses its energy, and that is giving rise to kinetic energy in the water. So where the water is moving with some velocity. Similarly, a brick lying on the ground. Similarly, consider a brick. You have a brick that is lying on the ground. A brick lying on the ground has potential energy 0. When it is lifted to certain height h from the ground, then the brick has some potential energy in it. A brick has a potential to hurt your feet. How? When it is at ground, it has a 0 potential energy. When it is lifted to certain height, I lift the brick from down to certain height. So that work is stored as a potential energy, and if I leave the brick, it will hurt my feet. So brick when it is at rest, has a potential energy 0. Similarly, consider an arrow attached to the bow. So it has a 0 potential energy. When I stretch the bow, so you can see here, when I stretch the bow, it gains. I'm doing some work in order to stretch the bow. It has some potential energy. When I leave the bow, it hits the target. So this potential energy which is stored is giving rise to the kinetic energy in future. So when I leave the bow, how it is going in reaching the target? It is because of the potential energy which is stored in the bow, which is giving rise to kinetic energy in the future. That is, it is allowing the bow to hit the target. Similarly, consider you have a spring. Spring has an elastic property. Rubber band spring has an elastic behavior. When you stretch the spring, so when you apply some force to stretch the spring, there is a work done because there is a displacement in the spring when you stretch it. So when the work done is stored in the form of potential energy. So when you stretch the spring, when you leave the two ends of the spring will come back to the initial position. How it is coming back to the initial position? It should have some energy in order to come back. When it is stretched, the potential energy is stored in the spring, so which is giving rise to the kinetic energy. When you release it, the spring is coming back to the original position. So these are the few examples of potential energy. It is the energy stored in a body due to its position or change in shape, or you can say position or configuration is called potential energy. So energy possessed by a body due to the virtue of its position or configuration is called potential energy. So example, you can see many examples. Water stored up at a height. Water stored up at a height. Water in the ground, water tank in the ground or brick in the ground doesn't have any potential energy. When it is lifted to certain height, h, so we're doing some force against gravity. We're applying some force against gravity. So the work done is stored in the form of potential energy, which will give rise to kinetic energy in future. So these are the few examples. Mechanical potential energy are of two types. We know mechanical energy are of two types. It's kinetic and potential. Now potential energy, mechanical potential energy are of two types. One is gravitational potential energy and another is elastic potential energy. We'll derive the expression for potential due to spring. That means elastic potential energy is there. So first is the gravitational potential energy. What do you mean by the term gravitational potential energy here? The energy possessed by a body. When you say a body, a tank or brick, it has certain mass. It has certain mass. So energy possessed by a body due to its position in the gravitational field is called as the gravitational potential energy, given by the expression U is equal to mgh, where m is the mass of the body, g is acceleration due to gravity, and h is the height. M is the mass. So what is g here? It is acceleration. It is acceleration due to gravity. It is acceleration due to gravity. So and what is h? It is height to which the object is lifted. It is the height. H is given by height. Now gravitational potential energy means it is the potential energy due to the position of the object. It is the potential energy due to the position of the object. Let us try to understand gravitational potential energy with an example. Consider the example here. Suppose you have an object. Say A. And this object, this body has some mass. Object has some mass, m. So initially it is at the ground level. And I am lifting this object A to certain height by h. I am lifting this object to certain height, say h, from the ground to certain point. So this object has mass. So when it has mass, there is a downward force acting, that is nothing but mg. W is equal to mg. So there is a downward force which is acting because the object A has certain mass, tank, brick has certain mass. So there is a downward pull. Due to the mass, there is a downward pull acting, downward weight acting, that is W is equal to mg. Now I have to pull, I have to lift this brick A or object A to certain height. So I have to apply a force against the gravity. I have to apply some force against the gravity, so to lift the object to height h. When the object is displaced from ground to certain height, I can say the work has been done. I am applying a force to lift the object, to raise the object from certain height h to certain height h. So I am doing work. So the object has displaced from ground to certain height. So work has been done. So that work done is stored in object A as a potential energy, as a gravitational potential energy, because I am applying force to lift the object. So because there is a downward force or downward force that is acting, W is equal to mg, due to the weight of the object. So I can write, how do you calculate work? W is equal to product of force and displacement, product of force and displacement. So what is the work that I have done in order to displace the object from ground to certain height? So what is the force? Force here is mg. So there is a downward force acting, due to which I have to apply some force to move the object against the gravity. So force acting is mg. So displacement is h. So it has moved the height h from the ground. I have raised the object to certain height h. So it is W is equal to mgh, or potential energy. The work done is stored in the form of potential energy. So it is U is equal to mgh. U is equal to mgh. You can see here it is U is equal to mgh. So m is the mass, g is the gravity, and h is the height to which I have raised the object. Similarly, this is about the gravitational potential energy. Whenever I lift the object from the ground level to certain height, so I have to apply force to raise the object against the gravity. So to certain height h, when I lift the object to certain height h, so work that I have done to lift the object is stored in the form of potential energy given by U is equal to mgh. Because the object has mass, we have studied in the previous session, there will be downward force acting. So you have to apply a force equal and opposite to this force to lift the object. So that is the gravitational potential energy. We know this is the conservative force which is acting on the object or the body, because we are telling gravitational potential energy. There is a gravitational force. Gravitational force is a conservative force, isn't it? Conservative force are nothing but those are the one which is independent of the path. The force depends on the initial and final. It depends on the initial and final position of the object. It is independent of the path. So it is a conservative force which is acting on the object. So what is potential energy? It is the energy stored in a body due to its position or change in shape is called potential energy. The SI unit for energy and dimension formula we have studied in the previous session, and there are two types of kinetic energy. One is the gravitational potential energy and another is the elastic potential energy. Another is the elastic potential energy. So that is nothing but elastic. When we say elastic, a spring comes into picture. A spring comes into picture. When you say elastic potential energy, when a spring has the elastic in nature, it has elastic behavior, a rubber band, etc. So when a spring is compressed or it is stretched, when it is compressed or it is stretched by an external force, that is the conservative force we are talking about, because spring force, gravitational force is an example for conservative forces. So a conservative force is acting on the spring. Restoring force is developed within the spring. This restoring force generated in the spring is called spring force. spring force. So we'll derive the expression for potential energy of the spring. You can see an image of the spring here. You can see if you have a spring, suppose this is your rigid support. Consider this is your, consider a rigid wall. Consider you have a rigid wall and a spring. A spring is nothing but a metallic wire. A spring is nothing but the metallic wire. One end of the spring is connected to the rigid support and another end you have connected a load, a brick or a block which has certain mass. So one end is connected to the rigid wall. Rigid wall means it will not deform. There will be no deformation in the wall. When you apply force on the spring, when you elongate or when you compress it, that force is not affecting this wall. So it is a rigid wall. There will be no any deformation in the wall. One end of the spring is connected to the wall and another free end of the spring is connected or given with some load which has certain mass. You can see the image here. So when this spring is elongated, you can see if this is the equilibrium position, if this is the equilibrium position, x is equal to 0. This is the rest state of the spring. It is the equilibrium position where the block is located. When the block is compressed or when it is elongated, you can see there is a displacement. There is the displacement in the block. This is the equilibrium position. So from here to here, the block has displaced. When you compress it from here to here, there is a displacement. When you stretch or elongate a spring, there will be a restoring force developed in the spring. We have studied in the previous chapter about the spring force. When the restoring force is developed in the spring, that will act in the opposite direction. You're applying force to pull the spring in this direction. So restoring force is developed in the opposite direction, which will try to bring back the spring to its original state. So that force, that restoring force developed within the spring is called spring force, given by Fs. So we'll derive the expression quickly for potential energy. So spring is initially, consider A. This is the rest state of the spring, where one end of the spring is connected to a rigid wall and another end of the spring we have put a load which has certain mass. So initially this is the equilibrium position of the spring, x is equal to 0. From here, in the next image you can see I am stretching, I am elongating the spring. So what happens? From the equilibrium position till here, there is a displacement given by x. From 0, it has displaced till point x. So there is a displacement. So we know in the spring force we studied, spring force Fs is directly proportional to minus x, because spring force is acting in opposite direction to that of force. Force is acting towards right. So restoring force is acting towards left. So they are opposite. So large the force applied, large will be the displacement. If I apply little force, little will be the displacement. If I apply more force, there will be large displacement. So this brick is placed on a horizontal surface which is a frictionless surface. We have placed this brick on a horizontal block on a horizontal surface which is frictionless. It's connected to the wall and another end we have put the load. When I stretch it with some force, when I elongate with some force, there is a restoring force which is acting opposite. So that restoring force, that's nothing but the spring force, is proportional to the displacement that have taken place. So restoring force is in opposite direction. That's why there is a negative sign here. To remove the proportionality constant, I'll write Fs is equal to, I'll add a constant of proportionality k and x. So to remove so it is minus kx, because restoring force is acting, spring force is opposite in direction. I have removed the proportionality sign and I have added k, proportionality constant here. K, what is k here? K is the spring constant. What is k? K is spring constant. If the spring constant is large, then the spring constant, if K is large, that means spring is stiff. That means spring is stiff. If K is less, spring constant is less, that means it is soft to stretch it. That means if K is large, the spring is stiff. You have to apply more force. So if the spring constant, that is K, if it is less, that means the spring is smooth. Less force is enough to elongate or compress the spring. So you see, K is equal to, it is minus Fs by x. To know the spring constant, K is equal to, it's minus Fs by spring force by the displacement that it has taken, it has undergone. So next, the force that we apply is proportional to displacement. That means if we apply large amount of force, there will be large displacement. X will be more. If you apply less force, the displacement will also be less. Now, when the spring force, when you apply some force, the spring is elongated. So what happens? There is a spring force, restoring force developed, which is acting in opposite direction to the external force that have been applied. So the spring force Fs will be minus Kx. It will be in opposite direction. Then I am applying force which is moving in forward direction. So the external force which I applied to stretch the spring, to cause the displacement of Ax is equal and opposite to the spring force. So F in forward direction will be equal to Kx, The force that I am applying here is not the constant force to elongate or compress spring. I am applying the variable force. Here. That means at each point of the motion of the spring, that is, the force acting is different. It is not magnitude of force is different. It is not constant. At each point of the motion of the spring, the force I applied is variable force. The magnitude is changing. It is not constant. So I cannot use the work done formula, that is W is equal to F dot S, because it is not a constant force. Then what is the work done formula for a variable force? For a variable force, it's integral from initial to final displacement f of x or f dot dx. So this is the work done for a variable force. In case of variable force, we are integrating the displacement from the equilibrium position to final position, from the initial position to final position, so that will give me the overall work done in order to stretch the string. I cannot use W is equal to F dot S. In case of constant force, you can use that. Here I am applying variable force. There is change in the magnitude of force at each point in the displacement of the string. So I am using the work done for variable force. It's integral F dot dx. So next, to find out the total work done on the string, first I need to calculate what is the small work done, that is dW. What is the small work done? That means what is work done? You apply force, there is a displacement of object, then you say work has been done. So I am applying variable force, there is a displacement of spring. There is some work done on this string in order to elongate. Now I have to calculate what is the work done, small amount of work done in order to stretch the spring to cause a displacement dx, to small displacement dx. So the work done by this force, a variable force, the work done by this force in stretching the spring small distance dx. So what is that small work done by this force, the variable force, in stretching the spring through a small distance x? The total distance of a stretching from equilibrium to the displaced point, it is x. So what is that small work done? So it is dW is equal to F dot dx. This is a small work done. Now I want the total work done in stretching the string from the equilibrium position till the displaced position. Now I want what is the total work done. What is the total work done in stretching the spring from equilibrium position, that is initially x was in the 0 position, from equilibrium position to a distance x, from 0 till x. What is the total work done by the variable force? So what you have to do, you have to integrate this equation 1. So you'll get dW is equal to, integrate from equilibrium position, from initial position to final position, final distance 0 to x, f dot dx. Now how will you integrate? Integration of dx is x, dy is y. Integration of dw is w is equal to integration from 0 to x. What is the force that I have applied? There is a spring force which is acting in opposite direction, that is Fs is equal to minus kx. So equal and opposite to spring force, we are applying external force in the forward direction. So the F is taken as, F is nothing but it is plus kx. You can see here F is equal to plus kx. Equal and opposite to spring force, there is a external force acting, that is in the positive direction. So F is equal to kx. F is equal to kx. I am just simplifying in this equation, work done for a variable force. It will be kx dot dx. K is a constant. So take out k, w is equal to k. How do you integrate x dx then? You have 0 to x, x dot dx. So I have taken k constant outside, you have x dot dx. How will you integrate? There is a formula to integrate x to the power n dx. How will you integrate this? X to the power n dx is nothing but x n plus 1 divided by n plus 1. This is a symbol of integration. Integration of x to the power n dx is given by x n plus 1 by n plus 1. Here you have x. If there is nothing to the power, that means x to the power 1 dot dx. So that is equal to x dot dx is nothing but x to the power 1. So you'll have x 1 plus 1 divided by 1 plus 1, that is nothing but x to the power 2 by 2. So integration, substituting that value x square by 2, integration 0 to x, 0 to x. So take out half is a constant. So take out half k, substitute x in place of x square and 0 in place of x. So I am substituting the limits in place of x. After substitution, I get it as x square. So the work done W is equal to half x square. So this is the work done by the spring in stretching the, this is the force work done by the force in stretching the spring to overcoming the spring force. So the energy spent in doing the work is stored as a potential energy. So the energy spent in doing this work, the energy that I am spending to do this work, to stretch the spring, it is stored as a potential energy. So this is the potential energy of the spring. This is the potential energy of the spring. This is for elongation. When you compress from the initial position, the spring will be displaced to the distance x. So from the equilibrium position, the spring is compressed. So it is compressed, so the distance is x. So when you calculate the force, the energy stored in spring is nothing but U is equal to half kx square. So you elongate or you compress, the force, the restoring force is same, U is equal to half kx square. So when you compress, opposite force acting, spring force, to bring it back to original position. Similarly, when you compress the string, there will be a, your force is acting in this direction. You are applying external force in this direction. It is plus kx. You are compressing the spring. But there is a restoring force which is acting in the opposite direction, in this direction. So this is the restoring force is equal to minus kx, because you are applying force in this direction, in the positive direction. So there is a opposite force that is acting that is the spring force which is bringing back the spring to normal position. So this is positive. There is opposite force acting to this external force, that is the spring force. So the potential energy, you stretch or you elongate or you compress the spring, the force, the restoring force is U is equal to half kx square. K is the spring constant. So this is the derivation for potential energy of the spring. So taking the work done for a small work done in order to stretch the spring through a distance, small distance dx. So this is the first equation. When you get to know the small work done, I want to know the total work done in order to stretch the spring of distance x. So what I'll do, I will integrate it from 0, from initial position, equilibrium position 0 to a distance, final distance x. So on integration, the force I am applying is in the positive direction. So it will be W is equal to half kx square. Next, you have law of conservation of energy. Energy is conserved. In the previous session, we studied the mechanical energy, conservation of mechanical energy. So mechanical energy is nothing but kinetic energy and the potential energy. The total mechanical energy of the system is conserved. Then what do you mean by this principle of law of conservation of energy? That energy can neither be created nor be destroyed, but it can be transferred from one form to another form. So the law of conservation of energy states that the total energy of an isolated system remains constant. The total energy of an isolated system remains constant. Energy can neither be created nor be destroyed, but can be transformed from one form to another form. What do you mean by converting the energy from one form to another form? Take the example of electric fan. Take the example of electric fan. Electric fan, the moment you turn on the switch, the fan starts to rotate. So the electrical energy in the fan, when you turn on the fan, the electrical energy is converted into mechanical energy. So what is happening in the fan? The electrical energy is converted to mechanical energy. You can see the energy is converted from one form to another form. Similarly, take the example of electric bulb. In electric bulb, you can see electrical energy. When you turn on the switch, the bulb starts to glow. How? The electrical energy is converted into light energy, which is giving you light. But here the energy is converted into two forms. So electrical energy in the bulb is converted into light energy plus some amount of heat energy. So the total energy of the system is conserved. So energy can neither be created or be destroyed, but it can be converted, but it can be transformed from one form to another form. Similarly, chemical energy is transformed to mechanical energy. You can see. So what is mechanical energy? It is nothing but the potential energy and the kinetic energy. So moving object has kinetic energy. So potential energy is nothing but the stored energy. It is the capability of the body to do something. It is the stored energy. So it is the energy possessed by the body by virtue of its position or change in shape. So when you elongate or stretch the string, elastic potential energy is the potential energy due to the change in shape. When you stretch or elongate the spring, there is a change in configuration. So that's all for today's session. In today's session, we studied about a potential energy. So it is the energy that is stored in the body. So a boy has a potential to score well in the exam. That is the potential, that is the capability of the boy to do something. So a brick in the ground has zero potential, but when you lift it to certain height of h, when it's stored at certain height, there's a work done which is stored in the form of potential energy in the brick. Similarly, we saw many examples. There are two types, gravitational potential energy and elastic potential energy. Gravitational potential energy is a potential energy due to its position. Elastic potential energy is a potential energy due to its change in shape. Next, we derived the expression for potential energy in a spring. It is U is equal to half kx square. When you elongate or compress the spring, there is a displacement in the position of the spring for the variable force you are applying. So it's a variable force you are applying. That means there is displacement. So we say work has been done. We calculated the work done in the stretching or elongating or compressing the spring. It is half kx square. The energy, the work done to stretch or elongate or compress the spring is stored in the form of potential energy, that U is equal to half kx square. Same will be in case of compression also. When you apply the force in the one direction, there is an equal and opposite force, that is spring force acting in the another direction. So next we studied law of conservation of energy, where we learned that energy can neither be created nor be destroyed, but it's transferred from one form to another. In electric fan, the electric energy is transferred to mechanical energy. Similarly, chemical energy is transformed to mechanical energy. So that is the principle of law of conservation of energy. Total energy of the system remains constant. We also studied conservation of mechanical energy, which works on this principle in the previous session. So next I'll come up with more session on work, energy and power, where we'll discuss in detail about the different forms of energy, heat energy, light energy, etc. And also we'll discuss what is power and what are the two types of collision. Until then, take care, have a good day. Thank you.